Okay, we are going to start studying logs and exponents. So the first thing we need to do is review our exponent rules. For example, if we have x with a negative exponent, I can change the power to the opposite if I move him downstairs. So you put x in the denominator and his power changes to positive. Not the x, but the exponent. If I take an x that has a negative exponent and move it upstairs, then the exponent will change to positive. What about if the exponent already is positive and I move him upstairs? Then the exponent becomes negative. So it becomes the opposite. What if the exponent is a fraction? Do you guys remember what this is? It's going to be a radical. So the denominator becomes the root of a radical, the bth root of x. Usually it's 1/2 and that becomes a square root, but it could be the cubed root as well. What if we have two bases that are the same? What do you do to the powers? Sometimes I remember this by connecting them with a line, and that looks like the start of a plus sign, s plus t. Here we have a base that has a power and then another power. A power to a power is very powerful, so we multiply. You can again start to connect these, and that looks like the start of a times sign. A power to a power is very powerful, so don't forget to multiply. What if you have two bases and they're in parentheses? So that s power is going to go to each of them. That's going to be x to the s times y to the s. That's not the case if it's x plus y. Then you have to write out x plus y times x plus y, I don't know how many times. Okay? Here, they each get the power. And anything to the 0 power is going to be 1. Let's give some examples here a try. Since the bases are both 2, we can go ahead and add those powers and make 4x. Here's a base with a power and another power. Those powers are so powerful we multiply. 3x squared. Here, the exponent is going to go to the things in the parentheses. So the 2 is going to stay outside for just a second. And that's going to make 9x squared. And 2 times 9 is 18. Some people say, do I distribute the 2? No, because that is just like a times, like a dot. The numbers get multiplied, and then you have x squared. All right, let's go ahead and move this upstairs so the power will become positive. I know the power is going to be positive 2. Now, when you move a negative 5 upstairs, he becomes, well, still a negative 5. The power is the one that changes. Okay, that's kind of tricky. That exponent does not belong to the negative. And here, you're going to raise something to the 0 power, but the only thing getting the 0 power is x. So that becomes a 1. 418 times 1 is 418. So that's just a brief review of exponents because we're going to need to know how to do those in order to make common bases. Here's a very popular rule. X to the power of s equals x to the power of t. And if they are indeed equal, and those bases are indeed equal, then, well, the power s must equal the power t. The exponents must be equal. When we make bases equal, since the equations are equal, then the exponents are equal. The exponents are equal, and that's kind of what we're going to do here with all these examples. Okay, so we've got an equation here. We're going to solve it. I've got 3 to some sort of power equaling 3 to the power 12, and they are indeed equal. Well, since they're both 3's, that means that the power x on the left must equal the exponent on the right, and that equation is solved. Okay, if you make common bases, it becomes very easy. Here we also have bases of 3, but we're going to have to do a little work on the right side first. I have to think of 81 in terms of 3 to the power of 4. Now they're both bases of 3. Okay, again, we're making common bases. That means that the exponent on the left equals the exponent on the right. So x equals 3. Okay. We're making common bases. I've got 1/7. I've got a fraction on the left. So I'm thinking that this is 1/7 sort of power as well. I know the 1 can become a 1. I don't think it's a 2. Let's see. Is it going to be a power of 3? Is 49 times 7 343? Go ahead and try that and tell me yes or no. Yes? Okay, great. That means that x equals 3. So what we did there is 1/7 times 1/7 times 1/7 makes 1 over 343. So fractions are just tops and bottoms. We're going to make some more common bases here. The common base between 2 and 4 is 2. You always go smaller. So I've got a 2 to the power of 18 on the left. I'm going to put parentheses around the 4. I'm going to change those parentheses. So the stuff inside the parentheses used to be a 4, and now the expression is going to be 2 squared. Okay, I'm close. At least I've got 2's. But now I notice that 2 has an exponent. He has a power to a power that's so powerful. What do? Yeah, we're going to multiply those. That makes 6x. Now that you've made your common bases, we can go ahead and say that 18 is equal to 6x, and so x must be a 3. Okay, so you always want to go smaller. Between 4 and 8, let's make a common base. Oh, but you can't turn an 8 into a 4, can you? So we're going to have to go even smaller. I have to make both of them have a base of, that's right, 2. So let's put parentheses around the 4. I'm going to alter him and parentheses around the 8. So I've got stuff in parentheses to the x. I've got stuff over here to the x minus 1. So let's rewrite 4 as 2 squared. And let's rewrite 8 as 2 cubed. Now we've got power to a power that's so powerful. So the exponent on the left is 2x. And the exponent on the right is 3x minus 3. We had to multiply those. Make sure you distribute. And so we can go ahead and solve this. I'll subtract 2x, and x equals a 3. You can go ahead and check this by taking the number and plugging it in up there. All right, let's keep going. Let's change, we'll change all these to a base of e. So I've already got e on the left. On the right, I'm going to have to bring this e upstairs. When you bring an exponent up, it changes to negative. The base stays the same. And now, let's see, this is multiply. When you're multiplying bases, what do you do to those powers? That's right, you're going to add them. Okay, so we have e to the negative x squared equals e to the x minus 3. So let's go ahead and isolate the exponents then. Negative x squared equals x minus 3. Let's move everybody to the right. That's x squared plus x minus 3. And go ahead and factor that one. What do you say? It doesn't factor? Well, then guess what we got to use? Quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So x is negative 1 plus or minus the square root of 13 all over 2. Wow, look at those answers. Okay, if you can't solve by factoring, then go ahead and use the quadratic formula. All right, let's keep making some more common bases. Here we're going to make some common bases of 3's. So let's bring this 3 upstairs. Let's do a power to a power is very powerful. So I'm going to multiply those, and I'm going to bring that one upstairs. So the exponent here is going to be 4x times 3 with an exponent of x squared equals 3 to the power of 12. Let's go ahead and combine these. You can't really set the exponents equal until you have one common base on either side. So what are we going to do to these exponents here? It's not a power to a power. It's not powerful, so we're going to add them. I'll say x squared plus 4x, just to put it in descending order, of course. Now, if you have common bases, then you have equal exponents. X squared plus 4x equals 12. We'll go ahead and bring the 12 to the other side, make him negative, equals 0. Does this one factor? It does. All right, go ahead and factor it then. I know it's got to be x and x. How do you make a 12? but it's got to add to positive 4. So I think we're going to have to do a positive 6 and a negative 2. So there are two answers here, negative 6 and positive 2. Okay, we got one more common basis here. We're going to make a common base of 4. So we have a power of x squared minus 7. And here, let's put parentheses around the 64. Just isolate that for a second. 64 is 4 cubed. So let's see. We got x squared minus 7. A power to a power so powerful you're going to multiply and make 6x. Common bases. That means their exponents must be equal. X squared minus 7 must equal 6x. Let's bring everybody over to the left. And let's see if you can factor this guy. I think it does. Since it starts with x squared, it's got to be x and x. To make a negative 7, we'll do minus 7 plus 1. So the answers are 7 and negative 1. Okay. Now the bell just rang, so I have to go teach you people live, but what you're going to have to do is open up the next video to watch exponential growth and decay graphs. Okay, I got to go teach you. Bye. Okay, we're back. We're going to do exponential growth and decay graphs now. If I do learn how to splice these together, then it will be one video. If not, sorry about that. So let's talk about exponential growth. Okay, first of all, we have an exponential equation here, a to the power of x. So the exponent is the variable. And whenever you have the a be more than 1, it's going to be growth. The a is the base. Okay, so let's maybe find some points here. For example, 2 to the x power. If you put 0 in, you're going to get a 1. If you put a 1 in, you're going to get a 2. And if you put a negative 1 in, then you're going to get 1/2. So let's see what exponential growth equations look like. 0, 1 is a special point that a lot of them have. 1, 2 is right here, negative 1/2, okay? So what's going to happen is they're going to start like this, asymptotic to the x-axis, and then they grow, and they grow, and they grow, and then they go like this, okay? As you move from left to right, they get farther and farther from the x-axis. And even if they're going down negatively, they're getting farther from the x-axis. Whenever your base is more than 1, then you're going to be exponential growth. All right, how does exponential decay look like? Decay is any time you have a base that is between 0 and 1. Okay, what that means is it's going to be a fraction between 0 and 1, not more than 1. 1/4 is a fraction, so let's plug in 0. 1/4 to 0 makes a 1. Plug in a 1, you get 1/4. Plug in negative 1, you're going to flip and become a positive 4. So what does this look like? 0, 1 is a special point. 1, 1/4. And negative 1 gets the 4. And so here's what exponential decay looks like. They start really tall, and then they decrease, 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 smaller, 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 asymptotic to the x-axis, but never getting to the negative side. As you go left to right, if you are getting closer and closer to the x-axis, then you're going to be called decay as you go left to right. Okay, so decay gets closer to x-axis. And let's go write a note over here. Growth gets farther from the x-axis. Okay, so let me ask you, if you can see some equations here, whether or not they're growth or decay. Okay, the first equation here, I notice an E. Okay, first of all, we have to remember, we have to learn what an E is. E is a number. It's kind of like pi. And he has the value of 2.718828, ... Okay, it goes forever, it's irrational, and it never stops. So if you have a number E, I guess we can think of this like 2. The exponent is negative, so let's write this as 1 over E to the power of x. And I notice that the base there is 1 over E, kind of like 1 over 2. If the base is a half, then we're going to call this one decay. All right, how about number 2? You've got 8/3 to the power of x. That fraction, that number right there, is more than 1. If the base is more than 1, we're going to call it growth. Growth. How about number 3? Let's go ahead and simplify that exponent first. Let's write this as something to the x power. If the exponent's negative, you're going to flip the fraction inside and get 3/8. That base, is that more than 1 or less than 1? Since it's less, we're going to call this one decay as well. And right here, let's go ahead and flip that fraction, make the exponent positive. This one is clearly going to be growth. Okay, we're going to practice drawing some graphs now by looking at the base, thinking about points, thinking about growth and decay. Okay, the first equation that we're going to look at right here, make this nice and big for everybody, is negative 3 to the x. I think what we're going to do first, let's graph the basic. Let's graph y equals 3 to the x, and I'll use a black pen for that. 3 to the x would be growth. They always have this special point 0, 1. He's going to be growing, 1, 3. Okay, here is basic growth. Now let's talk about the problem that they asked us to solve. This problem right here had a negative sign out in front. Do you remember what reflection that's going to be over? That's a reflection over the x-axis. So let's take this graph. Let's look at the x-axis. Anything above is going to be going down. So 0, 1 becomes 0, negative 1. 1, 3 becomes 1, negative 3. Okay, and here it is, reflection over the x-axis. This is still considered growth. It's growing away from the x-axis. Okay, let's do that again. This one right here, I'm going to maybe simplify before I go ahead and do it. So let's go ahead and make the x, the exponent there, positive. We'll have to flip inside, and I don't have to do a basic and then a reflection or anything. I'm just going to go ahead and graph exponential decay. Exponential decay, 0, 1. And if you'd like, you could plug in 1 and get 1/5. But I'm a little more accurate in my graphing if I plug in a negative 1 and get a 5. Exponential decay starts off really high and then sweeps down and starts to get smaller, asymptotic to the positive x-axis. Okay, let's go take a look at the third one here. 1/4 to the negative x power. Let's go ahead and simplify that one as well. I'm going to take 1/4 and make it be a 4 to the power of x. And so this is going to be exponential growth. Sometimes it's helpful if you want to write down points. So if you plug in 0, you're going to get a 1. If you plug in 1, you're going to get a 4. There you go, 2 points, and it's growth. So we'll plug in, or we'll plot 0, 1, 1, 4. It's asymptotic to the x-axis. Let's make sure we draw growth. There you go. Okay, this next one right here, this one's going to have some shifting to it. This x, or this number is by the x, so that's going to be shifting 1 unit to the right. Okay, but it might be helpful to take out a basic or a pencil, and let's graph y equals e to the x. And then I'll shift it 1 to the right once I have it on my paper. E is 2 point something, so that's going to be growth. So this one's going to be growth, and the special points are 0, 1, and 1, e. And e is about 2.71. So let's draw a basic growth, 0, 1, 1, e, 2.7. There it is. Okay, so here is e to the x. Now, if you're not switching colors, then you're going to have to do dotted one, a solid, or put some equations on your graphs, because my final answer here is going to be 1 to the right. So 0, 1 goes to 1, 1. 1, e moves to 2, e. Does the asymptote change at all? Does the asymptote? No, it's still the x-axis. It's just everything else is to the right. Okay. This last one here has some shifting to it. When you have 1/2 to the x, and then the 3 is after, do you guys know what that 3 is going to do? That's going to shift it 3 units down. 3 units down. But I think what I want to do is I want to see the basic 1/2 to the x first, and then I can go ahead and move it down with my green pen. So 1/2 to the x is decay. Make sure you think about growth or decay. Let's think about some special points. If you plug in 0, you're going to get 1. If you plug in 1, you're going to get a 1/2. That might be kind of tiny. Let's also plug in -1 and then flip that and get a 2. Okay, so let's draw a decay. 0, 1, -1, comma 2. 1 is only 1/2. Okay, so here's your basic decay. Do it in black or a light pencil, and now it's time for the final answer. Your final answer needs to go 3 units down. So if the asymptote used to be the x-axis, does the asymptote change? Yep, the asymptote has to go down 1, 2, 3. So let's draw an asymptote so you don't veer off too far. Let's take this point one at a time and move it down 1, 2, 3. This point here is in the middle. It's going to go down 1, 2, 3. And -1, comma 2 is going to go down 1, 2, 3. Okay, so here is my exponential decay approaching the new asymptote at y equals -3. Let me just refresh your memory. Here are some things that you learned in Chapter 2 that you might need to do when you're shifting and stuff. Okay? If we have negative square root of -x, this is how we studied it. If the negative is out in front, that is going to be a reflection over the x-axis. If the negative is inside by the x, that's the y-axis. So what's that going to look like for us? Exponentially speaking, if we have -5 to the -x power, this is the y-axis, because it's by the x, and this is the x-axis. Now you could also flip this number, do the reciprocal, and instead of y-axis, you would go from growth to decay or decay to growth. Okay? And then let's just recall what it looks like if we have the square root of x plus 2 plus 7. So here, inside, it's got to be the opposite. That would be left 2. And this one right here would be up 7. Okay, so what does that look like exponentially speaking? If we have y equals 5 to the x power, by the x would be plus 2. Okay, so that would be left, is by the x, and then outside afterwards would say plus 7, and that would be the up 7. So that's where things are